Morning, everyone. How are we doing? Questions while we wait for others to come in? Yeah, absolutely. We're going to finish up the material today. Questions in the meantime? How are we doing with triple integrals? Is this our last lecture? Well, that's the question, right? I mean, it's supposed to be our last. But, we're cutting it short in the sense that we are doing still new material today. So we can discuss that a bit later when everybody's here, whether or not we want a class on Thursday. We do a class on Thursday if everybody wants one. Right, Naloy, as you suggest, if you integrate with respect to z, you get a function of x and y. And then if you integrated that with respect to y, say, then you get a function of x and z. So it would really have to be, well, yeah, so you'd integrate that, and then you'd get another function of just x and z, and then you can repeat with respect to y. So you'd have three things happening. I don't think that gives us any real insight in. Yeah, so if we do add a class on Thursday, it's going to be at exactly the same time. I realize it follows a Monday schedule, but there's nothing we can do about that. So same time. It will, of course, be recorded. We will not learn new stuff on Thursday. Well, again, let's wait until everybody comes in. We can discuss it. We'll discuss it later on towards the end. Questions in the meantime? Correct. Thursday is a Monday schedule. All right. So Well, nothing is stopping us from having an extra lecture, right? Nothing wrong with that. We're not going to introduce any new material at that point. We'll just be to answer questions students may have, go over some stuff. It's like an office hour. How many questions are on the final exam? We did not write the final exam yet. Questions? Today we're going to talk about change of variables. Means let's postpone that. Just the setup, you say? Very well. Well, let's just set it up. Let's just set it up. So x squared plus y squared equals 4. You know what that looks like. This is a circle of radius 2 in the xy plane. And no z is specified, so you're stacking these in the direction of z, right? Up and down. And then you have this thing, 4x squared plus 4y squared plus z squared is equal to 64. First of all, observe that when z is 0, you can divide by 4 and you get x squared plus y squared equals 16, which is a circle of radius 4 in the xy plane, right? So it intersects the xy plane further away from this. And, I mean, if these were just ones, this would be a sphere of radius 8, but because of this, it's like an ellipse, right, in the xy plane, but now it's a 3D version of that, so it's an ellipsoid, right? I mean, a sort of egg shape, if you will, goes, right, when x and y are both 0, z is going to be 8, or negative 8, as opposed to this 4 here. So it's longer on the z-axis than it is on the x and y. So a football shape, if you will, kind of thing. Right, so what are we looking for? We are looking for the volume inside the cylinder and inside this football shape object. Right, so you see the idea. So let's set it up as a triple integral. If we set it up as a triple integral, you know the integrand is 1. Right, so we can set it up dz, dy, dx. How does z vary? Well, there's obviously symmetry, but if you don't want to use it, that's fine. When you're solving for z here, z is plus or minus the square root of 64 minus 4x squared minus 4y squared. So z goes from the bottom to the top, so the negative square root to the positive square root. Again, you can use symmetry if you want and say 0 to there and multiply by 2, that would be fine. Once z has been described, we project onto the xy plane, and obviously you get this disk of radius 2. So x squared plus y squared less than or equal to 4. is the projection onto the XY plane. Why did I leave it like this? I mean, I think it's clear that you're not going to want to integrate with respect to X or Y here, right? After you integrate with respect to Z, you're going to want to switch to polar coordinates. You're going to want to switch to polar coordinates afterwards. How do we get the 1 as the integrand? We're looking for the volume, as Charles suggests. All right. So today we're going to talk about change of variables in triple integrals. And, I mean, this is a nice introduction to that, right? Because here, once you integrate with respect to Z, the idea is to switch to polar coordinates, right? So Z remains as is, X and Y can be thought of as switching to polar coordinates. In other words, if you have any point in 3 space, right, you can describe any point by saying how far you go on the x-axis, how far you go on the y, and how far you go on the z. But you know that any point in xy can be described by saying how far you are from the origin and what angle that ray makes with the positive x-axis. And then you could bring everything up to z via z. So this could also be described using polar coordinates for x and y and just letting z be z. In other words, the polar coordinates for x and y and z remains z. This is known as cylindrical coordinates. Right, what are we saying? X is r cos, y is r sine, and z is just z. These are known as the cylindrical coordinates. If you are switching to cylindrical coordinates in the context of a triple integral, you know that you have to calculate the Jacobian. First of all, before we calculate the Jacobian, let me point out here r, right? R is measured from the origin moving out, and theta is measured from the positive x-axis counterclockwise. Adamar is asking why I've written this. Could I not figure out the bounds normally? Of course we could. Absolutely. We could figure out the bounds. I claim that you're not going to want to integrate with respect to y, right? Because once you integrate with respect to z, you immediately get to times this. Right? And if you integrate with respect to y, you're going to have to use some trig substitution, which is going to be a lot of work here. It's going to be better to switch to polar, so there's really no point in working out the bounds if your goal is to switch to polar coordinates anyways. All right, so So as Nikki suggests, cylindrical is really the polar coordinates in 3D. Absolutely. Let's calculate the Jacobian, which is dxyz by dr theta z, or dx dr, dx d theta, dx dz, dy dr, dy d theta, dy dz, and dz dr, dz d theta, dz dz. What do we get? Cos theta minus r sine theta, 0. Sine theta, r cos, and 0. And finally, 0, 0, 1. Absolutely. Charles knows what's coming up. Let's evaluate the determinant here by making a cofactor expansion along the third column. Plus, minus, plus, minus, plus. So this is going to be the same as 1 times this 2 by 2 determinant. Which is r cos squared plus r sine squared, which is just r. It comes as no surprise, right? Because it's really the polar coordinates for x and y. So Jacobian for the cylindrical coordinate transformation is, once again, just r. However, here's the thing. I never use cylindrical coordinates because I always do this. I set up my integral in terms of x, y, z. Integrate with respect to z, and then I switch to polar coordinates. So never do I set anything up using cylindrical coordinates. I'm not saying that's what you should do. I'm just saying I never use them. Because they are just the polar coordinates in x and y anyways. You could go straight to a cylindrical coordinate setup on the exam. Absolutely. Nothing wrong with that. And the book has some exercises. They want you to do that. And that's fine. You don't need to find the Jacobian. We did the Jacobian for polar coordinates. So if you're using a polar coordinate transformation, you can assume the Jacobian is r. If you're using cylindrical coordinate transformation, you can assume the Jacobian is r. We're going to do one more right now, the one that Charles was hinting at. The important one right, if you're given any point in x3 space, there's another way to describe that point. You can say how far you are from the origin. Let's call that rho. You can say what angle this makes with the positive x-axis. Let's call that theta. So very much like the polar coordinates, if you will. and how far down you've come from the positive z-axis, denoted as phi. So take this example here. Suppose the y-axis is like this, the x-axis is here, right? So really what the picture is, and I'll be the z-axis. And if you want to touch any point on the in 3 space, I mean, let's say this point right here. So here I am, the positive z-axis. I'm going to rotate to there, and then I'm going to come down, and the rho here is going to, it's the distance from the origin. So there it is, right? I mean, I rotated, came down, and I've touched that point. If we, let's say we want to touch a point, let's say this equal sign right here, right? So what could I do? I can rotate like this and then come down like that. What am I pointing at? The whole point here that I'm trying to make, right? I mean, there are 2 possibilities. You're thinking phi could rotate from 0 to 360, but you don't need to go that far. You don't need to go that far. You can restrict your attention to phi between 0 and pi. You don't need to go any further than, you don't need to go 360 degrees. You only need to go 180 to touch every point, right? Because you're allowed with theta, theta is allowed to spin 360 degrees. So, right, you don't need to go all the way down and come back up to touch that point. You're allowed to spin around. This might not seem important right now, but it's of crucial importance when we calculate the Jacobian. So what is this coordinate system? This is known as the spherical coordinates. And let me give them to you. Rho cos theta sine phi. Rho sine theta sine phi. And z is rho cos phi. You can work these out through triangles, right? It's just a little bit of geometry that I'm not going to go through because it's too long and doesn't bring anything to the understanding. Louis is correct that you could take phi to go from 0 to 2 pi and theta to go from 0 to pi, and there you could hit all points as well, absolutely. But let me show you why you don't want to do that and why taking phi in 0 to pi, theta in 0 to 2 pi, and restricting your attention to positive rho is useful because we're now going to calculate the Jacobian. Rho theta phi so rho theta phi, rho theta phi, rho theta phi. I would expect spherical coordinates to be in the exam. It's a very important part of the course. Tremendously useful for 264. You'll be using that over and over again in 264. So let's calculate the partial derivatives, the xd rho, cos theta sine phi, minus rho sine theta sine phi, and rho cos theta cos phi. dy d rho. dz d theta, there is no theta, so that's 0, and dz d phi minus rho sine phi. What is that? What are we going to do? Let's do a cofactor expansion along the third row. Plus minus plus. So this 2 by 2. Plus minus plus minus plus. Times this 2 by 2. Let's expand this. What do we have? Cosine this minus this. So minus rho squared sine squared theta sine cos. Minus rho squared cos squared sine cos. Minus rho sine times rho cos squared sine squared. Plus rho sine squared sine squared. if you factor out a negative rho squared sine theta, sine phi cos phi, present in both, you're left with sine squared plus cosine squared. Right, so we factor out a minus rho sine cos, so we'll have 2 outside, and this leaves us with sine squared plus cosine squared. And similarly, if I factor out a sine squared phi, I'm left with rho sine cubed, probably a rho as well. And it was actually rho squared that I should have factored out. Thank you. Thank you. If I factor out a rho and a sine squared, I'm left with cos squared theta plus sine squared theta. And as you know, these are both 1, so these disappear. And then if I factor out a negative rho squared, I've got 1 sine present in both, so let's factor that out. I'll be left with a cosine squared plus a sine squared. Phi this time, which is also equal to 1. And there it is. So when you make a polar coordinate transformation, you throw in the absolute value of the Jacobian, which is absolute value of this, and here's where phi being restricted to 0 to pi is important. Because in this region, in this domain, sine is positive. So the absolute value of this is just rho squared sine phi. And you don't have to worry about breaking up your interval to get rid of the absolute value of the Jacobian if you just make sure phi is always between 0 and pi. And you don't need any more to touch every point in 3D, right? Remember that phi is measured from the positive axis coming down. So you don't need to go past 180 degrees to touch every point, because if you want to touch this point right here, right, you can rotate and come down and extend. How are we doing here? So we have calculated the Jacobian of the spherical coordinate transformation. And again, you never have to calculate it again. Here it is. We've done it once. You can use it. Unless the question in the exam is asking you to calculate the Jacobian as an exercise, then you never have to do it. Does rotating influence the value of theta? I'm not sure what you mean by that. What do you mean by that, Samuel? Rotating so that phi is 0 to 180. I mean, phi and theta are completely independent. How do we determine the value of theta? Well, that's the thing, right? I mean, this is certainly a question that arises in polar coordinates as well. How do we determine the value of theta? So that depends on every single question. We'll take some examples. I mean, all we did now was calculate the Jacobian. Let's take a few examples. Exactly that, right? As Charles suggests, you're trying to describe a region. So up and down is independent of left and right, which is independent of back and forth. All right. Let's graph. Let's graph to understand the region E. What are we integrating over? Right, let's graph this thing. In the XZ plane, it's just a parabola. In the YZ plane, same thing. And then we put everything together via level curves, right? When Z is C, what do you have here? You have circles. So you put everything together with circles. Circles centered at the origin. All right. And then you have this, which you recognize as Z equals 4 is a plane. So you're cutting this thing with a plane. Right, so here it is. So, you have this bowl shape. And the region E is the whole thing inside, right? It's the region enclosed by the bowl and that top. Why do we have two curves? I don't know what you're referring to, Dan. Which two curves are we talking about here? Right, I mean, the question suggests an enclosed region. Well, I mean, but I'm still not sure what two curves you're talking about. Right, I mean, we have this bowl and we have this plane. If you only had Z equals X squared plus Y squared, the bowl would continue on forever. Well, I mean, this was coming from here, right? This was coming from here. This was the level curves to understand how to put everything together. Right, I started by drawing Z equals X squared in the XZ plane when Y is 0, right? And then I drew the same thing in the YZ plane when X is 0, and then we put everything together via level curves. All right, so let's set up our integral. Let's try setting it up, dz dy dx. In polar coordinates, your r starts at the origin. Well, I mean, r is measured from the origin going out, and same with rho. Rho is measured from the origin going out. How does z vary? Right, you see what's going on here. Z is going from your bowl to the top. Z goes from x squared plus y squared to the top. Why is it z now instead of 1? Well, I mean, we cannot change the question, right? The question is telling us z. In the previous question you're alluding to, we were looking for the volume. So we decided to set it up as a triple integral, and in that case, the integrand is 1. We could have set it up as a double integral, where the integrand would have been different from 1. We've described how z varies. Let's project everything onto the xy plane. And of course, you understand that since your bowl is getting larger and larger, the projection or the shadow cast onto the xy plane is going to depend on the intersection of the bowl and the top. So where do these two intersect? They intersect at x squared plus y squared is equal to 4. And so you have this great circle here. And so the shadow cast is going to be this disk of radius 2, center of the origin. So in the xy plane, the projection is the disk of radius 2. No point in setting it up dy dx, because you know what we're going to do. Right? We're going to integrate with respect to z first. And we get 1/2 z squared. Right? This thing, well, I mean, you could do that separately, right? That's just 8 times the area. It's just 8 times the area, so you can work that out trivially, or you can do the integral, it's all good. We're going to switch to polar. So you see, this page 1100 has to do with cylindrical coordinates. And they invite you to do the integral with respect to cylindrical coordinates. Like I said, not a fan of that, not going to bother. You can always switch to polar. So setting everything up in terms of cylindrical coordinates is the same as switching polar. So let's finish that up. If you switch to polar, what do we want to do? Well, so first of all, this is 8 minus 1/2. You know x squared plus y squared is r squared. So this is r to the 4. Jacobian, dr d theta, where r varies from 0 to 2. And you spin that around from 0 to 2 pi, thereby mapping out the whole thing. Mapping out your whole disk will could we do spherical here? I've conveniently erased it, but let me point out why you would not want to do spherical. You have your bowl, and you have this top, and you ask yourself, how does phi vary? Phi is measured from the origin going out. So phi goes from the origin to your bowl for a while until you hit here, and then phi goes from the origin to the top. So immediately you'd have to break it up into at least two pieces. And you probably don't want to do that. The integral is easy enough here. There's no theta anywhere. Let's integrate with respect to theta. And if you integrate with respect to r, this is 4r squared minus 1 over 12 r to the 6 from 0 to 2. Whatever that is. 16 minus 16 over 3. So that is 32, 64. 64 pi over 3. I didn't mean rho. I don't know what I said, but rho is what I meant. Rho is measured from the origin going outwards, right? I'm talking about this here. So you see what's happening, right? You'd have to split it up into two pieces, at least two. Exactly, right? I mean, you look at this and it's really screaming out cylindrical coordinates. Absolutely. That might be problematic when you have bounds that depend on theta, right? Be careful. Be very careful. So it really depends on your integrand. Here it's because we don't have thetas anywhere, so you're fine. But don't assume that to always be the case. You could have thetas. Yeah, exactly, Cam, right? I have never set up an integral using cylindrical coordinates immediately. I always just switch. That being said, those cylindrical coordinates are also very important. We won't have time to do the nice example, but I'm sure you'll do it in 264. Louis wants the nice example. It's especially nice if you're doing 2, 6, 3 simultaneously. You have a nice partial differential equation known as Laplace's equation, which says that So this is known as Laplace's equation. Show that Laplace's equation becomes yeah, I don't even know what it becomes. I don't want to write down the wrong thing. So I'll let you look it up. Becomes something in cylindrical coordinates. I want to. Can somebody look it up? I want to say. What do I want to say? D squared F by D R squared. I want to say 1 over R squared this plus D plus 1 over R dr, no, df dr plus D squared F by D theta squared plus D squared F by DZ squared. I could be way off. I could be completely way off. Can somebody Google Laplace's equation in cylindrical coordinates? It'll tell you what it is. While somebody's Googling that to make sure I haven't made any mistakes, let's take a moment to graph this. One over R squared. What about it? Should it not be there? Is there a coefficient that's incorrect? X squared plus y squared plus z squared equal to 9. You know what that is. That's a sphere of radius 3. And the less than or equal to means the whole thing inside. The coefficient of the first term, 1 over R squared. Yeah, I have that. 1 over R squared. Is it incorrect? Oh, coefficient of the term 1 is 1. There's no 1 over R squared. Like this. Thank you. Thank you. Possibly. I mean, did you look that up? Can somebody Google that? I mean, if you Google, it'll give it to you immediately, I'm sure. Laplace's equation in cylindrical coordinates. Well, I mean, now we're moving on to this, but I was hoping I'll find it myself. There's a 1 over r squared. 1 over r squared is here. There it is. Thank you. Yeah, so there's a nice example. Something everybody should do at least once in their life. Verify that in polar coordinates this becomes that. It's just an exercise in the chain rule. All right, sphere of radius 3, and what do we want? Just the y bigger than 0 part. So this hemisphere right, this right half of the sphere, just this right half of the sphere. Before I erase this, I'm sure you strongly suspect that there is a Laplace's equation in spherical coordinates. Much, much, much more difficult. I mean, it's not difficult, it's just much longer. I once gave this on a 264 final exam. All right. Let's set this up, dz dy dx, just for fun. I mean, it is an exercise in spherical coordinates, but nothing is preventing you from integrating with respect to x, y, and z. How does z vary? Right, z is going to go from the bottom half of the sphere to the top half. So z goes from the negative square root to the positive. Once z has been described, you would project onto the xy plane. And what is the projection onto the xy plane? I don't think it's clear. It's a half disk. Absolutely, thank you. Right, this top half disk. So let's set it up. How does y vary? Y goes, so first of all, it's the disk of radius 3, right? X squared plus y squared is equal to 9. So y goes from 0 to the square root of 9 minus x squared. And then you project onto the x-axis and you get minus 3 to 3. There it is. Like I said, nothing is preventing you from integrating with respect to z. That's very easy. Integral with respect to z, we get 2y squared square root. Now, however, you see the issue. The y bigger than or equal to 0, what is that? That does not interfere in the z. This just tells us that we're completely disregarding the left-hand side of the sphere. It's a half sphere, a hemisphere, just the right half. Right, and now you see the issue, right? You see that you wouldn't want to integrate with respect to y here, nor x. It's a lot of work, calls for a trig sub. We're not going to do that. You could switch to polar. That is possible, right? How do we describe this in polar? R goes from 0 to 3, and you're going to spin that around 180 degrees. So 2y is r sine theta. X squared plus y squared is r squared. Where r varies from 0 to 3, it varies from 0 to 5. But notice you have r cubed square root of 9 minus r squared. It's not too difficult to integrate. And then you have sine squared as well. I'll let you integrate that. Because our sphere is symmetric in all 4 octants, can we split the region into 4 and multiply our integral? Well, first of all, not considering, oh, you mean these 4 pieces? Yes, okay. Fine. You can do that, yes. I mean, you need to do a little argument on your exam, right? I mean, not only do you need symmetry of the region of integration, but you also need symmetry of the integrand. Well, I mean, again, the argument needs to be made. I'm going to let you finish that up. What I want to do is bring your attention to spherical coordinates. Let me not erase it. Let's switch to spherical instead. I don't know what the final answer is. I'm hoping it's going to be easier to do it in spherical. What is this in spherical? Y is rho sine theta sine phi. So it's y squared. Jacobian, rho squared sine phi. D rho, d phi, d theta, where phi, I mean, I keep calling it phi, but it's rho, right? Where rho varies from 0 to the sphere. So what is the sphere in spherical coordinates? Well, your sphere is x squared plus y squared plus z squared equals, in this case, 9. So let's figure out what that is in spherical coordinates. X is rho cos theta sine phi. Y is rho sine theta sine phi. And z is rho cos phi. let's simplify that. This becomes rho squared cos squared sine squared plus rho squared sine squared theta sine squared phi plus rho squared cos squared phi. When you add these two together, factoring out a rho squared sine squared phi, you get sine squared plus cosine squared. I'm going to erase that for convenience. I'll graph it again momentarily. Right, these two together give us rho squared sine squared phi. If you factor that out, you get a rho squared theta plus sine squared theta. And this is 1. So you get rho squared sine squared plus rho squared cos squared. But again, factoring out a rho squared gives you sine squared plus cosine squared. Let's take a moment to understand what happened here. In spherical coordinates, x squared plus y squared plus z squared is just rho squared. So in the same way that in polar coordinates, x squared plus y squared was r squared, here in spherical coordinates, x squared plus y squared plus z squared is just rho squared. So this complicated sphere that we had becomes a simple rho equals 30. Is there a problem where integrating in polar coordinates is harder than in dy dx? Absolutely. They're almost always harder, except if you're dealing with good regions, right? I mean, in particular, imagine that you just had a small rectangle here, A, B, C, D. If you want to describe this region in polar coordinates, I mean, it's not even clear that that's exactly where this would happen. Probably something like this. And anyways, I mean, my point is just take a rectangle. If you're integrating over a rectangle in x and y, do it in polar coordinates, you'll see that it's much harder. Right, so, I mean, in the same way as with polar coordinates here, imagine having a rod of length 3, and then you're spinning it around, right? First of all, from here all the way down 180 degrees. And then you're spinning that 360 degrees. You're going to map out a whole sphere. So if we're switching to spherical coordinates, right, we notice that x squared plus y squared plus z squared is rho squared. So we want to describe our hemisphere how do we describe our hemisphere in spherical coordinates? Well, your rho is going to go from 0 to 3, as we have just observed. We're going to rotate this 180 degrees. So phi is going to go from 0 to pi. And you're going to rotate this business another 180 degrees this way, so as not to hit anything in the negative y region. All right. So what are we looking at? 0 to pi, 0 to pi, 0 to 3. What do we have? Rho squared, rho to the 4. Sine squared, sine cubed phi. D rho d phi d theta. Why is it 0 to 3? Well, rho is measured from the origin outwards. So we ask the question, when do we stop? And you stop on the sphere. So we figured out the equation of the sphere. The equation of the sphere in spherical coordinates became rho equals 3. If it's, Gabrielle is asking if you have to prove this every time. Again, on an exam, you should prove it. Why is it 0 to pi, not minus pi over 2 to pi over 2? For which value? For which, Kevin? For which variable are you referring to here? Because I've got two 0 to pi's, right? Why did we rotate 180, not 360? We only wanted the hemisphere. Y bigger than or equal to 0. D rho d phi d theta. You can switch again, right? Fubini's applies here. You can switch, but I think this order is the best. Kevin is asking for phi. This one here. Well, I mean, phi is measured from the positive z-axis coming down, right? So you don't want, first of all, you never want to go past this because of the Jacobian, as we saw it. Moreover, you've got some stuff in the bottom half here underneath the xy plane, so you want to hit that as well. Theta is measured from the positive x-axis counterclockwise, right? So it's just in this upper half here, in this hemisphere, right? I mean, if you look at it in the xy plane, this is the region. So theta goes from 0 to pi. Marie's asking, how do we know which order of integration is the best? I think you can safely assume it's always d phi, d rho, d phi, d theta. So look, I mean, I've erased it, but you had an integral here, which we hadn't finished in polar coordinates. If you integrate it, and the integral is not too difficult, it's doable. Doesn't rely on trig substitution or anything, a simple u substitution. And I'll invite you to do this one. They have to agree. We're going to move on now because we're running out of time, but the integrals themselves are fairly easy, right? You know how to integrate sine squared. You're going to use the formula 1/2 1 minus cosine 2 theta, half angle identity, right? And for sine cubed, you're going to write sine cubed as sine squared times sine, and this sine squared is 1 minus cos squared. And then you're going to make a u substitution, u equals cosine. So evaluate those two integrals, make sure you get the same answer. Of course, you got to integrate with respect to phi first, right? Again, right, keep in mind that these spherical coordinates are only here to help you. If you don't want to use it, you don't have to. The previous question, you could have integrated with respect to x. It would have been, or with respect to y or x. It would have been a lot of work. A tremendous amount of work. But it's doable. Same thing here. Right? First, let's draw the region we're integrating over to understand what's happening. Let's start with this business. What is that? When y is 0, z is the square root of x squared, which is the absolute value of x. You know what that looks like. When x is 0, z is absolute value of y. And we're going to put all of that together by looking at level curves. And level curves are circles. So we have a cone. A cone that goes on forever, right? And then what is this? Well, you know what that is. That's a sphere of radius 1. And right, so you have a sphere of radius 1, and this is a sphere of radius 2. So there you go. What are we talking about here? E lies above the cone. and between these two things. So I think we're talking about this layer of ice cream, if you will, right? Imagine a cone with some ice cream in it, and then a second scoop above. Kind of thing. All right. Everybody with us? How we doing? Well, I mean, you see the issue, right? If you were to describe this in X, Y, and Z, Z would vary from here to there for a while until you hit this, and then it varies from the ice cream here to the ice cream there for a while, and then until you hit this, and then it varies from here to there. It's a lot of work. Let's instead switch to spherical. Why would you want to switch to spherical? Well, let's talk about how rho varies. Rho is measured from the origin going out. You see what's happening, right? Rho always goes from the lower ice cream to the top, from the lower sphere to the top. Lower sphere, which is rho equals 1, to the upper sphere, which is rho equals 2. Rho always varies. So first of all, we have this, which we just calculated in the previous example, was rho squared. So this is square root of rho squared. Jacobian, rho squared sine phi, d rho, d phi, d theta, where rho varies from 1 to 2. What about phi? Phi is measured from the positive z-axis coming down. How far down do you go? Well, you stop when you hit the cone. The cone tells you how far down you go. Right? Z is measured and you go down. I mean, phi is measured from the positive z-axis and you go down until you hit the cone. So what is the cone? The cone dictates your phi. Z is rho cos phi, x squared. X is rho cos theta sine phi. So this squared plus rho sine theta sine phi. What is that? Rho squared cos squared theta sine squared phi plus rho squared sine squared theta sine squared phi. And if you factor out a rho squared sine squared phi, which is present in both, you're left with sine squared theta plus cosine squared theta, which is just 1. So this is rho squared, what did we factor out? Sine squared, which is rho sine phi, right? Because you're restricting your attention to positive rho and phi between 0 and pi. And we're looking for when these two things are equal. If you cancel the rows, in other words, when is cosine phi equal to sine phi? This happens when phi is pi over 4. So phi equals pi over 4 is the equation of the cone, right? Very complicated in 3 space, in x, y, z, in Cartesian coordinates. Very easily described in spherical coordinates. Does this make sense? Right? Imagine going down pi over 4. No rho is mentioned, so you can go as far as you want. And no theta is mentioned, so you're spinning that around. So there it is. You've got your cone. There it is. How are we doing? So phi goes from 0 to pi over 4. And then you want to spin that 360 degrees around. Marie's asking how we obtain this. Well, we just plugged in the spherical coordinates into this, into the equation of your cone, and simplify it. Theta, right? So, I mean, again, we said we needed to spin that around 0 to 2 pi. There we go. Integrate. So you see that the integration is trivial here. Can we say y is absolute value of x rotates around pi over 4? Wait, are you using both x's, y's, and spherical coordinates all in the same thing there? Before anybody leaves, as we were discussing before the start of today's class, this is our last class, but you know, I mean, we're kind of rushed, and we actually have one more thing to do. So we'll have one last class on Thursday. Thursday, 11:30. Email me if you want an extension to the work. So Thursday, 11:30, we'll have one more class. Come armed with questions. We can do other things. Why doesn't phi go from negative pi over 4 to pi over 4? First of all, phi, we convinced ourselves that we were restricting the attention of phi to at most the interval 0 to pi because of the Jacobian. Otherwise, the Jacobian could be negative, and we certainly don't want that, right? Because we're taking the absolute value of the Jacobian. So, yeah. Secondly, you're thinking to yourself, you might want to go backwards, but you don't need to. That's the point, right? You only need to go forwards because the theta spinning it around 360 does the trick. Integration is trivial here. We can do that in our heads. This is phi cubed, so that is 1 over 4. Phi to the 4, so 16 minus 1 is 15. Antiderivative of sine is negative cos between 0 and pi over 4. And there's no theta, so that's 2 pi. So what is that? That is 1 minus 1 over root 2. So this whole thing is 15 pi 1 minus 1 over root 2 over 2. correct? Y equals x is an angle of pi over 4 when you draw it in the xy plane. Absolutely. Or your, well, I mean, right here. Yeah. Doesn't square root of rho squared mean absolute value? That's right. But here, you're in a positive region for rho, so the absolute value is not necessary. So we can use that to dictate our phi bounds. You want to be careful, right? Because what you've suggested is an angle theta being pi over 4 in the xy plane. We are talking about this angle right here. So I don't know that there's necessarily a relationship between the two. How are we doing here? So here's what I'm going to suggest. Perhaps a good place to end. You guys work on polar coordinates and we can discuss it in more detail. I mean spherical coordinates, and we can discuss it in more detail on Thursday. So we'll have one last class where we'll answer questions, and we actually have one last thing to do. In other words, another change of variables. I'll just give you one example. I mean, it's a nice example. To find phi, should we find an intersection somehow? We argued that how phi varies was dictated by the cone, right? Phi goes down until you hit the cone. So that's what told us the bounds for phi. Thursday, the same time as usual. Absolutely. Thank you all for coming, folks, and I will see you on Thursday. The last change of variables is just called that, a change of variables. There, right? I mean, we saw 2 cylindrical and spherical coordinates, but there are infinitely many others. And you can do a change of variables like you would do a U substitution in the regular one-dimensional case. So we'll just see other examples. But the whole point is, if you decide on a change of variables, Jacobian comes into play. That's all. Yeah, well, Thursday is just in general. Just in general, like a U substitution. We'll see how these sometimes arise naturally. You'll see. Don't worry about it for now. The important thing is the spherical coordinates. Everything else is much easier. Not that spherical coordinates is difficult. All right. Thank you all for coming, folks. I will see you on Thursday.